Hospital Anuradhapur to continue with the rest of the program. Thank you.
Good morning, everybody. Our first lecture is on overcoming interferences in spectrophotometric assays, and the speaker is Dr. Tushari Nanage, consultant chemical pathologist, teaching hospital Ratnapura. Unfortunately, Tushari is not joining with us today. Instead, we will be playing the recording sent by Dr. Tushari.
Sajja. B.
So it seems to be a technical problem related to this recording. So until we adjust that problem and we correct that, we will be continuing the program with the second lecture for today. So before going for the lecture, I would like to give an introduction to this lecture like this. You will be happy if you obtain a higher mark than your colleague at the exam. But if you obtain a higher value from your analyzer, then it's counterpart. So Dr. Tushara will be answering this question. He will be presenting on method comparison. Dr. Tushara is the consultant clinical pathologist, teaching hospital and Radioactive. Over to you, Dr. Tushara.
Okay, good morning, everybody. We had an interference with the lecture on interferences, unfortunately, so I have to took over the job now. My lecture is method comparison. And the scope of my lecture is going to be www.how. I will be talking on what, why, when, which, and how in relation to method comparison. Method comparison experiment will judge the agreement and the correlation between two methods. The agreement is when you have an acceptable bias or acceptable difference. The correlation is when you have a predictable or an identifiable relationship between the two methods. I mentioned about two methods. So what are these two methods? They include the candidate methods, which is the new method, and the comparative method, which is the existing routine method in your lab. You will be doing a method comparison experiment when you have changed your old method with a newer one, or else when you have installed a new instrument. Sometimes you will be doing the same to evaluate a new method. You have obtained your value from one method or one analyzer, and you expect your MLT to reproduce the same thing on a different analyzer on a different method. And now you understand why did I include proficiency testing also here. Sometimes you will be comparing two existing methods in your lab from time to time. Whether the method is old or new, all your instruments and methods have already been validated in the sense that the manufacturer's claims on accuracy, precision, sensitivity, specificity, and so many other things have already been confirmed by a third-party agency before they come and get installed in your lab. Then, why do you want to compare two methods? To answer to that, I will get on to the error model. If I take internal quality control sample as an example, it has an assigned value given by the manufacturer, which is the true value. And you will be repeatedly analyzing this and obtain the target value, which is the mean value, right? So you obtain the mean value of your repetitive measurements, and that becomes your target value. Your target value is equal to the true value only with the reference method, which is very specific to that method. But in all your field methods, your target value vary from your true value because of the bias, which may be the random bias or maybe the mean bias or the systematic bias. Your random bias, it varies in the intensity and the direction from one sample to the other, whereas your mean bias has a constant intensity and the direction. Your mean bias is the inherent difference between the two methods, whereas the random bias results from the sample matrix difference, the temperature fluctuations, instability of the analyzers, and pipetting problems. If I take a simple example, creatinine Japanese method is often 10 times higher than the cytotoxic method, and that 10 times is the mean bias. And any different from that 10% is the random bias. Now, I told you that your target value is the mean value of repetitive measurements. But whenever you analyze your internal QC, for an example, you will not obtain sharply your target value. Instead, you will be within plus or minus 2 SD from your target value. So I would say the measured value equals the target value plus or minus 2 SD. And that 2 SD is your random error. So finally, I can say that the measured value equals true value plus mean bias plus random bias. And this bias varies from one method to the other. And this is why method comparison is. I have given you the main steps in doing a method comparison, which I'm not going to read because I'll be taking one by one. First thing is to choose the comparative method, which should be the best method in the laboratory. And ideally, it should be the reference method, but often it is going to be the routine method in your lab. Whenever possible, your comparative method should have an analytical range as wide as the candidate method. And you should be using the same units as the candidate method. And it should be free from common inferences and should be having a bias which is known to you. You have to be familiar with both methods in relation to its operation, maintenance, troubleshooting, and quality control. The measuring should cover the clinically important range, and at least 50% of your samples should be above and below the laboratory reference interval. Sampling should be done in accordance with the manufacturer's recommendation, and you have to collect an adequate volume to permit repeat analysis if necessary. Storing of a sample is best avoided, and if you do, you have to follow the manufacturer's recommendations. The NCCLS guidelines recommend to include at least 40 samples to a study, but in most of the practical situations, the number of samples is restricted to 20. It's better to have some additional samples because you can make some allowances for the data that is going to be discarded as outliers. And also, the higher the number of samples, the stronger your statistical conclusion is. Rejection and acceptance should be done as recommended by the manufacturer, and any rejection should be documented with reasons. A method comparison experiment should be done. All samples should be analyzed within a time frame which is compatible with the stability of the analyte, or within 2 hours of collection, whichever comes earlier. Both methods should be having a reasonable quality controlling. I mentioned that your experiment should be done over 5 days. However, at the end of each day, you have to plot your data on a plant or plant and look for outliers. Had there been any outlier, you have to reanalyze that sample. And if still remain an outlier, that data should be discarded. Coming to data analysis, which is the most important part. You have the candidate method giving its values for each and every sample, and you have the comparative method giving values for each and every sample. And now you can obtain the mean value between the candidate method and the comparative method for each and every sample. At the same time, you calculate the difference between the candidate method and the comparative method for each and every sample. And now we are in a position to calculate your mean bias, the standard deviation of the bias, and 1.96 SD of the bias. And now you can plot your data on plant or plant. And I'm not going to read this because this chart is going to do that. That is plant or plant plot, which got the mean value of the candidate method and the comparative method on the x-axis, and the difference between the 2 methods on the y-axis. In addition, you have to draw the 0 line. On this line, the bias is 0. Above that, there's a positive bias. Below that, there's a negative bias. You have to draw the mean bias line and 1.96 SD lines. And when you plot your data, your plant or plant will look like that. I mentioned that the x-axis is the mean of the 2 methods and not the value obtained from the comparative method. Why is that? Because your comparative method is not the true value, it is not the reference method. So to make the x-axis as close as possible to the true value, you obtain the mean value. So that is the idea of having the mean on your x-axis. But what? If your comparative method is the reference method, now we are getting the true value, and there's no reason why you obtain the mean value. You can straight away plot your comparative method obtained from the reference method on your x-axis, and the resulting plot is known as the true plot. Now let's see how to interpret this, whether it is plant or plant or true. You look at your data point and see whether they equally scatter around the 0 line. If it is, That means the number of positive biases are equal to the number of negative biases, which is a good thing. Then you look for a trend and any outlier sitting above or below 1.96 SD lines. That is a Plant-Altman plot for you to interpret. Try and quickly interpret this. So you can see your data points, the blue ones, equally scattered above and below the zero bias line, which is a good thing. But after 300, there's a clear negative bias. So I would say that the two methods are agreeable up to 300. Another Plant-Altman plot for you to interpret. Again, you can see your data points scattered equally above and below the zero bias line, which is a good thing. However, there's a rising trend for your positive biases as well as for your negative biases, which is not a good thing. Because when there is a trend like this, what happens? Your bias is increased at higher concentrations. T-test is another statistical approach which is used to find out the agreeability between two methods. And the recommended testing method comparison is two-tailed paired t-test, which is done on Microsoft Excel or on SPSS. If the probability value that you obtain is less or equal to 0.05, it is statistically significant and it indicates a poor agreement. Coming to linear regression. On your x-axis, you have the comparative method value, and on your y-axis, you have the candidate method value. When you plot this on a computer, it will automatically give you the regression equation, the regression coefficient R, and the coefficient of determination R squared. And the plot is interpreted in relation to its slope, y-intercept, regression equation, regression coefficient, and the coefficient of determination. The regression formula equalizes your y value to slope multiplied by the value on your x-axis plus the intercept. So what do you mean by this slope? It is y value divided by x. In other words, when you change your x by 1 unit, how much change would be there for your y? And your slope in a linear regression indicate the proportional bias between the two methods, and it is due to the calibration difference. The ideal slope is 1. In our case, our slope was that, which means the two methods had a proportional bias of 0.09%. What do you mean by the y-intercept? It is the distance between the x-axis and y, where the regression line meets y. And it indicates the constant bias between the two methods. And it is due to calibration difference at the set point. In our case, our intercept was that, which means when the comparative method value was 0, we obtain a value of that much for the candidate method. Your regression coefficient and the coefficient of determination indicate how close your results to the regression line are. They range from -1 to +1. A good correlation is indicated by a regression coefficient above 0.975 or a coefficient of determination above 0.95. The ideal R or R square is ±1. If you see a negative R, that indicates a negative slope, which means there is an inverse relationship between the two methods. You can see two regression plots. Look at the top one. Your data points are nicely sitting on the regression line, which means there's a very good correlation, which is reflected by a good correlation coefficient. Look at the below one. The data points scattering away from your line. A poor correlation, which is reflected by a poor R and R square. So if your R or R square is low, that indicates a poor correlation, but at the same time, it could be due to inadequate range of sampling, or maybe due to individual samples with interferences. So you are supposed to do more sampling and exclude any outlier. The regression equation is used to calculate the bias at different concentrations, particularly the bias at medical decision-making points. And then you compare your calculated bias with the allowable bias obtained from standard literature. Even here is an example. The decision-making for our analyte glucose is 126 milligrams per deciliter. Now I am going to check if the comparative method gave a value of 126, what would be the value that I am going to obtain for the candidate method. So what I have done here is I applied 126 to the index and I obtained that value, which was rounded up to 126, which means when the comparative method value is 126, the candidate method value is 125. And now I am in a position to calculate the bias between the two methods, including the percentage of bias, which I did. And then I obtained the allowable bias from clear guidelines and compared that with my bias, and I came to the conclusion that the bias of the new method is allowable at the medical decision-making point. A linear regression plot for you to interpret. You can see your data points nicely sitting on the line, and there's an excellent R and R square. And look at the regression equation, y equal x, which means zero bias. So it looks a very good study. However, you have not covered that area, so you should not be reporting this. Right, you can see two regression plots. They look alike. Now take the left-hand one. Your data points nicely sitting on the line, and there's an excellent R. And look at the regression equation. Your y equals x, which means a zero bias. So that is a very good study. Now look at the right-handed one. Again, your data points sitting nicely on the line. Look at the R, excellent. But if you look at the regression equation, your y equals 10 times the x, which means when your candidate method value is 10 times higher than the comparative method. But the two plots look very much alike. So now you understand how misleading a linear regression would be. With that, I come to comparison of qualitative methods. For an example, comparison of HCG strips, which give a value either as positive or negative. You follow the same procedure as above, except the data analysis part, which is done with Cohen's kappa statistics. Right, so this is what I did. I obtained the values for both strips as negative or positive. Then I highlighted the discrepant values. And now I'm in a position to make a confusion matrix like this. So I'm not going to explain this because you can go through this later and understand. Anyway, once you make your confusion matrix, you are in a position to apply that data to the kappa equation given there. I did that. Again, I'm not going to explain this because you can go through this later and understand this. The kappa value which I obtained was 0.53, which I compared or interpreted against that. Now just look at these wordings: moderate, fair, slight, less than chance agreement. So none of them sounds nice. So I will take that substantial agreement, which means a kappa value of 0.61 to 0.8. And this value indicates that 61 to 80% of your data are correct and agreeable. But at the same time, it means that 20 to 39%, or I would say nearly 40% of your data are faulty. Yet there is substantial agreement. That is very funny. For this reason, now many textbooks recommend to obtain 80% agreement. Right, with that, I come to comparison of qualitative method with the quantitative method. For an example, you have the property strip giving values as negative or positive, and you have the auto analyzer giving an exact value. So what I did was, I know the cutoff point for a positive test for the auto analyzer, which is that. And using this value, I converted that values into negatives and positives. Then I followed the previous way and analyzed the data with kappa statistics. Those are my references, and thank you very much.
Thank you, Dr. Tushar, for your excellent presentation. Participants, if you have any questions, there's 5 minutes more. You can direct your questions to Dr. Tushar, and he's happy to answer your questions. Yes, you can post them in the chat box. So, in the absence of any questions, we would like to proceed with the next lecture. And to moderate the session, I would like to invite Dr. Tushar Hewagigana to continue with the rest of the program today. Thank you. Over to you, Dr. Tushar.
Right, we have changed our schedule a little bit. And before I introduce the next speaker, let me read this, which I obtained from Sunday Observer last week. Upcountry Godu parents looking for a suitable partner for their pretty daughter, age 27, height 5 feet, BSc graduated teacher, Kuja in 7th house. Please reply with horoscope. Now this is a specification for a bride's groom. The idea is to pick up the most suitable person. If you have the wrong person, that will be the end of your life. And selecting an analyzer is not difficult. if you choose the wrong analyzer, it will be the end of your lab and probably the end of your professional career. Good morning, Nadine.
Good morning, Dr. Tushara. Nice introduction.
Dr. Nadine Senanayaka, consultant chemical pathologist, District General Hospital, Vavuniya, is going to talk to you on factors considered in writing specification for fully automated biochemistry analyzer and reviewing tenders. Over to you, Nadine.
Thank you. Thank you, Dr. Tushara. Good morning. Today, I'm going to talk about factors that should be considered in writing specifications for an fully automated biochemistry analyzer and how we are going to review the tenders. First of all, I want to tell before the beginning of my lecture, this totally depends on the institution that you are going to select the automated biochemistry analyzer and the workload of the analyzer. I'm going to discuss about the factors that we considered in writing specifications. I'll divide those factors into two broad types. One is general factors and other one is specific factors, which are specifically designed for the institution that we are going to select the analyzer, and then the reviewing tenders. General factors, as you all know, the power supply in our country is 230 volt. It can be plus or minus 10% and 50 hertz. And there should be a UPS also. Optimally functioning temperature of the analyzer should be between 80 to 30 Celsius, and the humidity is 20 to 80%. This is because we can easily achieve this temperature and the humidity by an air conditioner. And the analyzer should be a brand new one. We have to mention that, otherwise they will give reconditioned analyzers that will give troubles to the operator. So we have to mention that the analyzer should be a brand new, and you can select whether it is a benchtop or a floor standing model according to the space and the workload of the institution. And it should have a random access, batch and stat analysis. And there should be separate arms for reagents and samples to avoid carryovers and interferences. The analyzer, these are the general factors I'm going to discuss first. The analyzer should have the facility to continuous loading and unloading of the samples and reagents. What I mean is some analyzers, if you want to load samples or you have to refeed the reagents, analyzer will stop its functioning, and it will take another half an hour or more to start it again. So there should not be such a thing. Otherwise, it will be time consuming. So the analyzer should have a facility for continuous loading and unloading of the samples and reagents. Even though you are going to load reagents for a specific analyzer should continue its work without stopping. And it should be covered, fully covered, to prevent dust entering into samples and reagents. And the analyzer should be able to dilute samples on board. And we should be able to decide the dilution factor It should be vary from 1 to 2 to maximum of 1 to 40. Those factors should be operator dependent, and there should the analyzer should have a non-touch vortex mixing capability, that is to avoid sample carryovers. The unit should have facility of onboard refrigeration for reagents under the temperature of 2 to 8 Celsius. It should have the capability of clot detection, and they have to, the bidder should include the calibration procedure and the stability of the calibration. It is better, the stability of the calibration has more duration, because frequent calibration will need more reagent, and it will ultimately affect the 5-year post-analysis in the tender procedure. So stability of the calibration, it should be at least 1 to 4 weeks, and calibrated traceability should be available, and unit should have the facility of storage, quality control data, as well as the ability to validate patients' results before production of the respective patient's final report. That is for the accuracy and the precision of the patient's data. And there should be a complete and detailed set of operation and service manual, which should be in English language. Warranty for a period of minimum of 12 months from the date of successful installation on full part and labor basis. Such warranty should include servicing and preventive maintenance during the period of validity. And there should be certifications such as ISO 13485-2003 or FDA or CE. There should be, they should mention about any other parts or accessories or consumables that are essentially required for a complete function unit and their price, because those things are needed to calculate the 5-year cost of the analysis. And the bidder should be able to provide the backup analyzer. It is better if they can provide a backup analyzer for continuous function of the laboratory. And they should provide necessary training to the instrument operators and certify to chemical pathologists with confirmed reporting training. And there should be time-to-time refresher training also, because most of the time MLTs are changing within the institution, as well as there will be new MLTs coming to the laboratory. So there should be ongoing refresher training which are done from the company itself. The unit should capable of measuring absorbance using suitable photometer unit to perform endpoint kinetic, and it should include the detection of substrate depletion and turbidimetric measurements in UV and visible range at constant temperature, that is 37 Celsius, with a minimum of 8 wavelengths, which should be between 340 to 650 nanometers. The unit should have cooling facilities capable of producing final test result without intervention of the operator. It also should have the facility to prevent evaporation of samples and reagents. it should have it may have a washing system with recyclable crates and facilities for scanning the crates and banking. Those things should mention whether it use the recyclable crates or disposable crates. If so, if it is disposable, they have to give the cost for the disposable crates. And it should use a sample cups which have a minimum capacity of 0.5 milliliter of sample volume. If it is pediatric, if we are going to use it for pediatric units, it should be lesser than that. Better if it is lesser than that. It should have facilities to detect liquid levels to ensure minimum sample and reagent dead volume. That is also is important for pediatric samples, as well as when we are calculating for QCs, because as you all know, we are dissolving the QC and then we are allocating them. So the dead volume of the machine should be included when we are allocating the QCs. Otherwise, the volume will be not sufficient for QC running, daily QC running. And the unit should have continuous wet auto washing facility by using a pre-warm detergent without interrupting the session for samples and crates, and carry out automatic blanking. That is for if the machine is using recyclable crates. If the machine does not use recyclable crates, then this statement will not include in the, will not belongs to the bidder. And there should be facilities for computer-based management system, data input and storage of minimum of 30,000 test results with patients' data. This value can be vary depending on the workload of the institution. 30,000 test results may be less or more depending on the institution workload. And there should be a method of transferring such data onto a CD for storage, and storage of quality control data, ability to validate patient results using quality control program. And there should be a way to print out the patient's final report. And some companies offer free of charge printer, and some may otherwise we have to pay for it. So if so, we have to pay for it. They have to mention especially the price of the printer. And the other thing is whether they are going to offer us, give us the laser printer or a dot matrix also matters. And there should be facility to produce a hard copy of the patient's final report, including calculated data and the reference ranges. Additionally, there should be following facilities: printing device to get the final report, monitor display, and the UPS. The price of these units with necessary connections and software should quoted separately and should include they should be included in the 5-year cost analysis, which is done in the at the end of the tender reviewing. It analyzer may be open or closed system. If it is better if it is open system, which can produce accurate test results using reasonable good quality reagents. If the equipment needs specific operational requirements and environmental conditions or deionized water system, they should be clearly mentioned in the offer and quoted separately for such arrangements. Deionized water system, some bidders give offer it free of charge, and some need we have to pay. So this should be mentioned clearly in the tender. The local representative should sign a service agreement for at least 4 years after the period of warranty, and the cost for such contract should be mentioned. Contract shall give all the required details such as number of preventing services, the ability to provide backup system and on temporary basis. As I have told you before, on-site training for operation and maintenance of the machine is a necessary and must. And bidder shall furnish the documentary evidence to meet the following financial requirements, that is annual turnover not less than 100 million. The value can differ. And their net profit should not be negative for last 3 years. That is for the company stability, to take an idea of the company's stability. And the bidder shall furnish documentary evidence to demonstrate that it meets the following, their experience requirement. At least 4 full-time technicians should be available. Minimum of 2 technicians trained by the manufacturer. Other one is fully equipped workshop facility should be available with all tools and equipment required to maintain the machine. And also at least 5 years experience in supplying and maintaining medical equipment should be there. Documentary evidence to demonstrate the following usage requirement should be available. That is ISO CE certificate for good manufacturing practice, and availability of the brand in government hospital is preferable, and the availability of spare parts, consumables, and reagent extra. When we move on to reviewing tenders, following factors should be considered. Those the factors that I have already mentioned can be divided into compulsory and non-compulsory factors. That should be decided by the technical committee. Compulsory factors, all the bidders should fulfill the compulsory factors. Then we are, for example, if there are 8 bidders and only 5 bidders fulfill all the compulsory factors, the 3 other bidders we are not going to consider. We are going to consider the 5 bidders which have fulfilled all the compulsory factors. So the technical committee should mention clearly whether the specifications that they include are compulsory or not compulsory. Depending on the compulsory factors, even if a bidder doesn't have one compulsory factor, we may have to reject it because it is compulsory. So mentioning whether it is compulsory or not is a must, and it should be done carefully when we are writing a specification. Compulsory factors, other thing is the compulsory factors may be compulsory for one institution or may not be compulsory, it may not be compulsory for another institution. All these factors and the specifications that I have been mentioned earlier may change depending on the institutional level. And then we are going to select the instruments or the bidders that have fulfilled all the compulsory factors. After that, we have to calculate the 5-year cost for each analyzer. and we have to consider cost per test, service agreement cost, and the maintenance cost. And if there is any waste management or water supply, if we have to if you have to pay for those things, we have to add those cost of also for the 5-year cost analysis. And calibration frequency, QC frequency should be considered in the analyzing when we calculating the cost per test. QC frequency, also calibration QC should included for cost per test, not only for the reagents. I have mentioned those things again here. When calculating cost per test, following factors should be considered. That is cost for reagents and cost for QC, and depending on the frequency of the QC, and the calibration frequency and the stability, and cost for any other expenses used for analyzing, that is diluents, detergents, quotes, cost for waste management. And you have to pay attention for the open shelf life of the reagents and the other chemicals used for analyzing, and compare with the daily or monthly workload of the institution. And some reagents, when we open, we can keep it for 3 months, some may less than 3 months, or like that. And some companies have reagents, vials that we can do from 1 vial, we can do 50, and there are same company, they are having vials which can done 100. So depending on the workload of the institution, if you are going to select an automated analyzer for an institution which have less workload, if the company has reagent vials which can be done less amounts of sample from 1 vial, that will be a favorable factor for that bidder, because reagent wastage, we can minimize the reagent wastage from that factor. And we can get a feedback from the relevant people that have experience with the analyzer, such as we can contact the consultant chemical pathologist in the institution where the same machine is installed, and also from MLTs. For clarification, if there's more clarification needs other than the specifications that we have mentioned in this tender, that means we have to clarify. That means if there is specification that we have mentioned and we want to get more details from the tender, so if so, we can contact the tender through the tender committee, and we can get the written information. We can't add new specifications. We can get the clarifications what they have given to us for our specification, what we have already given. And there is a pre-bid meeting. That means before we considering the analyzing the details that they have given, there are pre-bid meetings. From at that meeting also we can take any clarifications that we need, and after the all, we can select the best analyzer that suits for the particular institution, and it may not be the lowest cost analyzer in the tender. That means even though the analyzer is lowest cost, we may not select the analyzer depending on the other factors. That means cost is not the main factor. The take-home message that I want to give you is we may need to include all the general specifications such as the power, humidity, and those things. And specific specification should depend on the institutional requirements, not the may differ what I have written in earlier, because it depends on the institutional requirements. And when selecting the analyzer, we have to consider all the factors, not only the cost. Thank you. So I may have to answer. I would like to answer any questions if there is.
Thank you very much, Naveen, for that interesting presentation. Now the session is open for questions. If you have any doubts or queries, you can ask Dr. Naveen. Or you can put it in that chat box there. Okay, there are no questions, it seems. So we will shift to the next session. Okay, we are moving to the next lecture. Hazards are everywhere, and your laboratory is no exception. Therefore, precautions and safety measures are important. As chemical pathologists of Sri Lanka, we have an additional hazard of having two sisters from the same family being in the field of chemical pathology. And one of the sisters is with us today. Good morning, Ganga.
Good morning. Hope you can hear me.
Yes, we can hear you. Dr. Ganga, consultant chemical pathologist from District General Hospital, Matara. She's going to talk to you on biosafety in clinical laboratory. Over to you, Ganga.
Thank you. Thank you, Dr. Tushara. First of all, good morning. First of all, I would like to convey my sincere thanks to the College of Chemical Pathologists of Sri Lanka for giving me this opportunity. During the next half an hour, I would like to share my knowledge regarding laboratory safety. As healthcare workers, we are at a higher risk. Why? Because all of us come in contact with patients, and we handle blood, body fluids, and infectious specimens, and we perform invasive as well as non-invasive procedure, and we handle sharps, and we get colonized with antibiotic-resistant hospital pathogens like MRSA. So laboratory safety is important. Why? The clinical laboratory has various types of hazards. The people working in the laboratory must know the various types of hazards in the laboratory and should know the possible precautions to avoid those accidents. And these dangers can be reduced by eliminating hazards where possible, establishing clean, safe, and safe work habits, taking proper precautions, and maintaining awareness of safety practices. What are the possible sources of injury in the laboratory? There are physical agents and sharp needles, chemicals, bacteria, and radioactive materials are the main possible sources for injury. When we take physical agents, wet flow and heavy boxes can cause injuries like sprains and falls simply. And sharp instruments like lancet and damaged glasses can cause punctures and cuts. Fire and explosives from burners and chemicals, workers can get burns. Chemicals like reagents and preservatives are most of the time carcinogenic and they have some toxic effects. Electrical hazards are wet equipment, ungrounded equipments and irregular electric cords where you can get electrical shock. Biological hazards are bacteria, viruses, parasites, and fungi. And there is a sorry. Can you hear me? You can get this infections and materials like radioisotopes and radioactive agents can get radiation injury. Let's discuss about fiscal hazards. They are common not in laboratory, in any working environment, and it's need to be avoided. You should avoid running inside the laboratory and be careful when the floor is wet. Take care while lifting heavy objects. Wear closed toe shoes and provide maximum support. Try to keep the working area neat and clean and keep the working area well organized. Sharp instruments are sharp edge instruments like needle, broken glasses, lancets can give rise to hazards like cut and prick injuries and bloodborne infections. You have to dispose all these sharp edges articles into a sharp bin made out of metal containers and should be kept in a safe place. Beakers, test tube, and flasks with broken edges should be removed from your working environment. When we consider the fire and explosives, when explosive and volatile chemicals are used in the chemical pathology laboratory, and flammable chemicals should be kept in the safety cabinet and explosion-proof refrigerators. Keep the compressed glass cylinders away from the heat. And whenever fire erupts, you have to rescue anyone in immediate danger, activate the institutional alarm to communicate, close all the doors of the fire area and try to extinguish the fire. According to the type of the fire and explosive, the extinguishing material is different. If the fire is due to wood, paper, clothing, you can use water. But if it's due to organic chemical, you can't use water. You have to use carbon dioxide or halon mixture. That means carbon dioxide, bromide, and bromine mixture. If it's a combustible metal, you have to use sand. Electrical, if the fire is due to electrical leakage, you can use carbon dioxide or halon mixture. These extinguishing materials should be available in the laboratory in case of fire emergency. Let's discuss about chemical hazards. As you know, strong acids and alkalis are the most common corrosive chemicals. And chemicals should be labeled as carcinogenic, poisonous, or corrosive. In the case of chemical spills, the best option is to flush the area with water, but remove the contaminated floors as soon as possible. NFPA 704 gives the color coding for the chemicals. What is NFPA 704 symbol? The National Fire Association has developed a color-coded number system called NFPA 704. This system uses a color-coded diamond with 4 quadrants in which numbers are used in the upper 3 quadrants to signal the degree of health hazards in blue color, flammability hazards in red color, reactivity hazards in yellow color, and if there are some specific hazards, it's in white color. So this is the NFPA 704 symbol. You may see this in the laboratory, but I think we are not much concentrating regarding this diamond-shaped symbol. This is the symbol for nitric acid. Health hazards number in blue color, fire hazards in red color, and instability hazards in yellow color, and if some specific hazards which we mentioned in white color. I think when you are doing the mixing of chemicals, you should be very careful. When mixing the acid and water, take water and then add the acid slowly. You have to, I think most of us practicing is, otherwise in addition, when there is addition of the acid, there will be heat production. Therefore, never add water to acid, and you have to slowly add acid to water. Toxic fumes. There are due to solvents from fumes or vapors. Some are toxic, and extracts with the fluorinated hydrocarbons, chemicals that causes damage to the liver. Some solvents causes bone marrow depletion, leukopenia, thrombocytopenia, and anemia. And some are carcinogenic as well. In case of the organic solvents, you have to use when you are handling the organic solvent, you have to use the foot and work in a well-ventilated area. You have to avoid contamination of the skin because these can get absorbed slowly via the skin. And you have to wash immediately with soap and water if there is a contamination. What are the carcinogens? Carcinogens we can encounter during laboratory work. The original list of occupational safety and health standards published in 1974 pointed 13 carcinogens, and this is the list of the 13 carcinogens. Some are familiar to us, and some are using as components of reagents and preservatives. These are the 13 carcinogens published, pointed in 1974. Regarding radioactive materials, I think you are familiar with the symbol, the radioactive material. This is needed in case using radioactive materials like radioisotopes, like in radioimmunoassay laboratories. Most radioactivity in the laboratory is very minimal and very little danger. Should avoid exposure to pregnant ladies because that will cause harm to the fetus, and the ladies who are expecting should avoid much such areas of radiation as well. When we consider the electrical hazards, it can happen in a laboratory because many equipments working on electricity. So we have to avoid wet hands to operate the equipment, and we have to look after the damaged wires and avoid overloading the circuits. If any equipment becomes wet, then immediately unplug the wires and let them dry before using it. If accidents occur and someone has an electric shock, immediately shut off the electricity without touching the person or equipment, and close the circuit breaker and move the equipment with some non-conducting objects like wood or glass. Let's discuss about biological hazards. Laboratory staff is always exposed to source of potentially pathogenic microorganisms, and hospitals are always filled with sick patients, and some of them have contagious diseases. Most of the samples like blood, body fluids, urine, CSF, and tissues have pathogenic organisms. Therefore, personal hand washing and wearing personal protective equipment are very important when handling specimens. The spread of infection may be by direct contact with the laboratory staff with the patient sample, or by inhalation of the infected material, like droplet infection, or if you are centrifuging the tube without capping it. So it's important to cap the tubes when you are centrifuging the sample, or by ingestion of contaminated food and water. Special precautions are needed while handling the samples of patients with hepatitis B virus, hepatitis C virus, and HIV viruses, because we can get bloodborne infection. Therefore, we have to wear gloves while collecting the blood from the possible causes of HIV, hepatitis B, and hepatitis C infected patients. And you have to wear face mask if there is any possibility of the splashing of blood or other body fluids. Dispose of all the sharp needles and objects in the puncture-resistant container. And you have to follow the universal guideline, universal precautions when you are handling sample patient infected with hepatitis B, hepatitis C, or HIV. You never recap the used needle, better to dispose of it or follow the direction given in the diagram, but it's better not to recap the needles. Most important in the case of prick or bleeding, you don't stop the blood immediately. The best is to bleed under the tap water as much as possible, and then use disinfectant and stop the bleeding. What are the 5 steps? There are 5 steps of universal precautions. I hope you already know these steps. Education, hand washing, use of protective barriers or personal protective equipment, cleaning of contaminated surfaces, safe handling, disposal of contaminated materials. What are standard and transmission-based precautions? They are the primary strategy for minimizing the transmission of healthcare-associated infection. Standard precautions must be used when providing care to all patients, regardless of whether they have an infection or not. Standard precautions include hand hygiene before and after every episode of patient contact. I hope you are familiar with 5 moments of hand hygiene. I will briefly explain it later. The use of personal protective equipment or PPE, and safe use and disposal of sharps, routine environmental cleaning, processing of proper processing of reusable medical equipment and instruments, respiratory hygiene, aseptic non-touch technique, waste management, and appropriate handling of linen. In spite of many developments in medicine and asepsis, hand washing is still the best solution. Hand hygiene is the simplest, most effective measure for preventing hospital-acquired infection. These are the 5 moments of hand hygiene. You have to wash hands before touching patient, before clean or aseptic procedure, after body fluid exposure is after touching a patient and after touching patient's surrounding. This slide shows how to wash your hands properly. You have to wash your hand using soap and preferably in running water. And after washing the hand properly, you have to dry your hand using a clean towel. This slide shows the 5 steps for a safe hand wash. First, you have to wash your palms, then back of the hand, then in between fingers, fingernails, and thumbs. When we consider the personal protective equipments, there are several personal protective equipments like caps, masks. There are several masks from simple surgical masks to K95 masks, and then the gowns, aprons, goggles, boots, and there are so many types of personal protective equipments in the market, and the selection is depend on the task allocated. Vaccination of healthcare workers are very important. All healthcare very important to prevent the infections. All healthcare workers are immunized against hepatitis infection at the time of recruitment. Hepatitis B is a course of vaccine given 0, 1, and 6 months of duration. After 1 month of the primary course, all healthcare workers will be tested for hepatitis B immunity status. Records the vaccination and immunity level of all healthcare workers are kept by the infection control officer ideally. Healthcare workers with inadequate immunity need to be periodically tested or give boosters because need not to be periodical testers or give boosters because hepatitis B virus provide long-term immunological memory. Immunocompromised people like HIV patients or hemodialysis patients under hemodialysis need monitoring of antibody levels and to get the boosters. Defaulters, if a healthcare worker has taken only 1 dose and presenting after 1 year, he or she should need to restart the full course. Otherwise, no need to restart, just continue the course. Pregnancy is not a contraindication for hepatitis B vaccination. Special vaccines are given in rabies reference lab. All healthcare workers engaging the lab work should be immunized against rabies. And in regional reference laboratory, polio regional reference laboratory, all healthcare workers will be given booster dose of OPV at the commencement of work. Above all, personal habits are very important to minimizing the risk. Personal habits play a large role in minimizing hazards. As you know, do not eat, drink, smoke, chew gums, or apply cosmetics, or insert contact lenses while in the laboratory. Do not store foods or beverages in the lab or in the chemical refrigerator. Do not mouth pipette. Wash hands before leaving laboratory or after handling contaminated materials. So when there is an exposure, you have to promptly detect and treat the exposures. There should be first aid in the laboratory. As first aid, you can wash with soap and water or flush. Then you have to document it. You have to document the incident, and you have to assess the risk by the risk assessment team, and then you have to do the post-exposure management. Depending on the type of exposure, source and contaminating material, management would vary. As first aid, there should be eye showers, body showers in the laboratory. These should be available. I would like to remind your memory regarding when there's a spill, biological spillover, how do you act? I think these steps are familiar, and you can go to this diagram. And there should be a spill kit available, and disinfecting or the hypochlorite agent should be freshly prepared, and this spill kit is or should be always available in the laboratory. I hope you have some idea. I share my knowledge regarding laboratory safety with you, and thank you so much for your patient hearing. If you have any question, you can ask now.
Thank you, Ganga, for that excellent presentation.
Yes.
And now the session is open for any questions. If you have any doubt or queries, you can ask Dr. Ganga.
Post to chat box.
Yeah, if you have questions, you can put it in that chat box.
Hello.
Hello.
Hello. I'm Dr. Shanali here.
Yeah.
Dr. Ganga.
Yeah.
I actually missed like the first few slides. I'm sorry if I'm like asking something that you have already shown in the presentation.
Right.
Just wanted to know because now this if this biosafety includes about fire safety and all that as well.
Yes.
In our laboratories, most of the like the fire extinguishers and everything,
Not,
even though they are there, they are mostly
not
expired.
Yes. Yes.
So,
Yes.
I mean, according to my knowledge, these, fire extinguishers, they have to be sort of replaced after a regular period of time, which
Yes.
is not sort of happening in our laboratories.
Hmm.
And like, I don't know, maybe in all these private sector labs, they have their sort of fire drills and everywhere where, you know, people are sort of educated about how to act in a fire situation, but in the government sector, we do not have any of this. So what is your opinion regarding this?
Yes, safety. The concern regarding laboratory safety, I also feel that it's not much appropriate. No, not much sufficient. And
Yes.
most of these showers and all, they are not working. And actually, monthly, I think monthly, we should have a checklist, and we have to check whether these safety materials and equipments are working, and all the plugs and electricity supply is safe for use. So that's my opinion, but I don't know whether this is applicable, how it's practical for our working environment, but it should happen.
Yes, okay, thank you.
Hello, I'm Dr. Dulani, chemical
Yes.
pathologist from Sandy.
Yeah.
Yeah, this is regarding, because this is a part of accreditation process.
Yes.
So safety, if we are going for the accreditation and if we are practicing that, that should address it. The main
Yes.
fault in our government sector that we are not adhered for that accreditation process.
Accreditation, yes. Therefore, the government sector laboratories are not much concerned on this aspect.
Yeah, the most
That
of
may be the reason.
The standard are not practicing, but it should be there in the ideal laboratory. That
Yes. Yes.
Hello, Dr. Ganga.
Yes.
Anything that from our college we can do sort of to educate our trainees and the working staff about this,
Yes.
say fire
Yes. Yes.
safety?
My personal idea is actually we have to educate the all staff categories of the laboratory staff, because if there is an accident, there should be a responsibility for all the staff members and how to act. One person's misbehavior will be a mess. Therefore, I personally think we should have some education programs regarding laboratory safety for all, not for the doctors, for all healthcare workers, all laboratory workers according to their education level. That's my suggestion. What do you think, Dr. Tushara? Can you hear me?
Yes, Rama.
Yes, he's asking for. I think we can arrange something. We will think about it. Tisari Ganga.
Okay.
I hope you can hear me. I think we will just think about it, creative something to arrange some workshop or some video or something.
Yes.
Yeah, I think we can do something. We just think and let you all know. We will try to do something with your help,
Yes.
Ganga. Okay, thank you for the suggestion.
Okay. Thank you so much for giving me this opportunity. Thank you very much for your patient hearing and very motivated questions.
Right. Any more questions? Okay. In the absence of any more questions, we'll have a break of 15 minutes, and we'll start our session after the break around 10:45. And during this break, we will be trialing that recording, which was sent to the college by Dr. Tushari. So this is just a trial, so you don't have to worry about that.
We can start 10:50. No, it's 10:45 now.
Okay, we will start at 10:50, right? So during the break, we will be trialing the recording, so you don't have to worry about that.
Good morning. I am Dr. Tushar. Chemical pathologist from Teaching Hospital Ratnapura. Today my talk is on overcoming interferences in spectrophotometric assays. This is my overview, basics of spectrophotometry, interferences.
Tushari, I think you're
Hello.
joining with us now.
Hello.
Hello. Right.
Hello.
Okay. Thank you very much for that interesting presentation. Now the session is open for questions. Dr. Tushar is there. If you have any queries.
Dr. Tushar, hello. Dr. Tushar, can you hear me?
Yes.
Actually, I'm recovering from influenza infection. So
Okay.
I have a difficulty in speaking continuously.
Right.
If there's any problem, please let them know to talk to me over the phone next
Okay.
week or email me.
Right.
I'm having difficulty in speaking. Okay,
Okay.
thank you.
Okay, thanks. Right. Okay, so if you have any queries, you can email or you can personally speak to Dr. Tushari later. Right. Now we'll get on to the last lecture. Good morning, Dilinika.
Good morning, Tushara.
Dr. Dilinika Pereira is the consultant chemical pathologist attached to Sirima Bandaranaike Specialized Hospital for Children. She is going to speak to you on analytical performance specifications. Over to you, Dilinika.
Thank you very much for your kind words of introduction. I hope you can see the slides.
We can see Dilinika.
Yes, okay. Good morning, everybody. Next 20 to 25 minutes, I'm going to talk about analytical performance specifications. So in overview, introduction, and what is the requirement for these analytical performance specifications, and what are the parameters we used in analytical performance specifications. I'm going to talk about those on those topics. So why we need these analytical performance specifications? So what are these performance specifications? Those are set of performances evaluated thoroughly before method adopted for routine use. I think you had a good lecture with Dr. Tushar for method comparison. And so there are certain performance specifications have to be fulfilled in order to have the method for routine use. So these performance specifications are guided by a set of guidelines. And so what are we going to evaluate is the precision, accuracy, analytical measurement range, etc. So I will discuss each one separately. So what is the requirement for these analytical performance specifications? So one thing is it is clinical need for introducing a new method or new analyte into your laboratory. And sometimes we need to evaluate new analyzer or instrument in the chemical pathology laboratory. And on the other hand, sometimes we have to improve the accuracy or precision over existing method. And so thereby, what are we going to do is to improve the diagnosis, treatment, and the risk stratification of the patient. Sometimes we can reduce the laboratory cost. So what are the guidelines available is Clinical and Laboratory Standard Institute, that is CLSI guidelines, and there are ISO guidelines. So before I am going for this analytical specification, the parameters, so I think you heard about these terms. So one term is the qualitative concept and the error you can see. The trueness is the closeness of agreement of mean value with the true value. The associated error with the trueness is the bias. So a measurement of the systematic error. The precision is the concept. So precision could be divided into repeatability and reproducibility, and the associated error with the precision is the imprecision. So that is a measurement of dispersion of random errors. So the accuracy is the closeness of agreement of a single measurement with a true value. And so the error measurement is comprised of both random and systematic error. So we are going to the specifications. So what are these analytical performance specifications? So that is the calibration, accuracy, precision, analytical range, or we known as linearity, and limit of detection, limit of quantification, analytical specificity or interference studies. First, we are going to talk about calibration. So what do we mean by calibration? So that is the relationship between the instrument signal and the concentration of the analyte. So that measured by samples with known quantities of the analyte, such as calibrators. So this, for that calibrators, we use the pure chemicals, and these calibration functions may be in different types, may be curved or linear, depending on the type of analyte. And especially for immunoassays, there are some special forms that is modeled by the 4-parameter logistic curves. So we know there are different methods. So it could be reference method or a field method. And in modern days, so we use, most of the laboratories, we use fully automated biochemistry analyzers or hormone analyzers. So this relationship between the analyte concentration and the signal is often very stable. So I don't think we have to do more calibrations nowadays, and it is like almost need very infrequently, sometimes maybe interval of several months. But we have to keep in mind when there is failure of quality controls, or when you are using a reagent like a new reagent kit lots, on that occasions, depending on the situation, we have to use the calibration. But in not always, when there is quality failure, you don't think always there is a calibration failure. So you need to find the root cause according to your problem. So this is a linear calibration curve, and this is the dose response curve for 2-site immunometric assay, and this is the calibration of competitive radioimmunoassay. And then we are moving to trueness and accuracy. So I have already discussed earlier also trueness. So trueness is the closeness of agreement between the average value and a true value. So how do we take this average value? Is from the large series of results of measurements. And the difference between the average value and the true value is expressed as the bias, and it is inversely related to the trueness. So the error comes with the trueness is the bias, and it is inversely related to the trueness. So accuracy is the closeness of agreement between the result of measurement and the true concentration of the analyte. So this is usually influenced by both bias and imprecision, and it reflects total error, and it is inversely related to the uncertainty of the measurements. So when you're talking about the trueness and the following concepts also important. One thing is recovery, drift, and the carryovers. So what do you mean by recovery? So the recovery is the fraction or percentage increase in concentration that is measured in relation to the amount added. So we add amount and we check for the how much is we can recover, right? If it is like 100% recovery, so there is a high degree of trueness, but it does not mean that it is unbiased. Why? There may be some effect against the matrix components. So there could be some interference substances that is not detected by the recovery experiment. So that you have to keep in mind. And this is one way we can do the recovery. So we'll add analyte, add water, and we will calculate as a percentage of recovery. So the drift is caused by the instrument stability over time, so that calibration could be biased due to the instrument problem. So that is the drift. And the carryover is from the high concentration sample to the next low concentration sample. But nowadays it is very rare, because there are good methods for washing and it is advanced technique. So it is carryover. Nowadays we can't see much. So it is close to zero to ensure the unbiased results. Precision is the next this specification. The precision is the closeness of agreement between independent results of a measurement obtained. So the error is the imprecision, right? It is expressed as standard deviation or coefficient of variation, is known as CV. And it is imprecision is a random error of measurements, and this is no relation to the trueness of the measurement. So precision is specified as two categories, repeatability and the reproducibility. So what do you mean by repeatability is the closeness of agreement between results of successful measurement. So this one carried out under same conditions during short interval time in one laboratory, possibly it's one operator using the same equipment, right? So it's like within one precision. So it is same conditions, same operator, same analyzer. And reproducibility is also the closeness of agreement between results of a successful measurement, but it is performed under change conditions of measurements, such as maybe time, operator, equipment, calibrators, and reagent lots. So two terms, reproducibility and repeatability. And in reproducibility, so we can divide into within laboratory reproducibility, and the other one is interlaboratory precision. So the within laboratory reproducibility is measured by running quality control samples over a period of time. And interlaboratory precision is between laboratory precision observed in external quality assurance schemes, and it is not the component of a method validation performed by a single laboratory. So this is important in consideration in the method selection and in evaluation process. So two things for reproducibility, within laboratory reproducibility and interlaboratory precision. So coming with this one, there's another term known as total SD, right? So, and this is, you can see this divide into within run and a component using the variance. So variance is the square SD. So the squared SD is the variance. So you can see how we take the total SD. So with within run and between run. So other important thing is, what are the test materials we can use in this precision testing? And it could be quality control samples or pooled patient serum. You can take from several patients, separate the serum and put into one pool and take it as a pool. So the number is given for precision studies are 20 observation, at least 20, but it depends between different guidelines. And if you use more observations, the more certain the estimate could be. And precision may be vary with analyte concentration. So it is important to find out the precision at least 1 or 2 concentrations. So when you are going to detect for precision testing, select medical decision-making concentration. That is important. So we need to find how imprecise this technique when you're using in the medical decision-making concentrations. So one other term is precision profile. So this precision profile is the presentation of precision as a function of analyte concentration. So you can see this chart. So this analyte concentration is plotted. So you can see the standard deviation and the CV. So SD is constant in this scenario, and it is independent of the concentration. It doesn't matter the analyte, even though the analyte concentration is coming up, the SD is, it is constant, but the CV is changing. So there are certain conditions and important we are using it. That is important to find the method specification over analytical range considered, and limit of quantification detection and method comparison study. So it is important, this question profile, when you are using for method comparison studies. And so we need to find over this when you are checking for analytical, this range. So there are certain other graphs. I have put only one type of thing. So it depends. So this is one type of graph I have mentioned there. So one of the important thing you should know, what do you mean by total analytical error? So the total analytical error comprises of random error, analytical error, and the systematic error. So the total analytical error is with the random error is coming with the precision, and the systematic error comes with the accuracy. So we are moving to linearity. So the linearity or analytical measurement range, so that is the relationship between the measured and expected value over the analytical measurement range. So that ideally, it should not be without any modifications. So we should not perform any it is without dilutions, right? So that the test we can perform without any modifications, example, dilutions, right? So that is very much important for high degree of trueness of the method. So how can we demonstrate it? So we can take the series of samples with known concentration, maybe calibrators, and space over analytical measurement range. And so other one is we can take a high concentration sample, we can do a serial dilutions, and it has to be with an appropriate sample matrix, especially in human serum. It could be individual or pool serum, and preferably in duplicate. So preferably duplicate to make the best fitted curve. If you do it in a graph, so if you do it in duplicate, we can plot a best fitted curve. So for immune chemical techniques, 6 or more calibrated standards we need with appropriate sample matrix. And so this confirmation of presence of linearity, whether this is linear, this method or not, we can carry it out by different ways. One method is a graphical plot of data. This is a very simple, and there are certain statistical tests will detect whether this method is linear or not. So, so many biochemical methods, the relationship between the measured and the expected values is linear with the stated range, and immunoassays, I have mentioned earlier, so it will be curved. And when you're using the range, you have to detect the clinical reportable range, and the range and like which are very clinically significant ones we have to use. And so we can report it following modifications such as dilutions. And it is important we have to decide the upper limit with the clinically reportable ones. Otherwise, there's no point we are doing very high concentration in this situation. So what do you mean by analytical sensitivity, right? So analytical sensitivity is the rate of change of the measured response with the change of the concentration or amount of the analyte. So the greater the sensitivity, the slope or the gradient of the calibration curve, we can see that if it is great. And what do you mean by this one? So we can able to detect small changes in the analyte concentration, right? So that is important. We can detect the small changes in the concentration. Compared with the analytical sensitivity, what do you mean by analytical specificity? right? So analytical specificity or the interferences. So this is able to detect the assay procedure to detect the target analyte, right? So they need to detect target analyte without influences from the other interference substances in the sample matrix, right? So especially the photometric measurements affected by presence of lot of colored sample compounds present in the sample or the substance which is physically similar, right? But practically, we can't we can't detect each and every interfering factors, but we can look into some common interference in substances such as hyperbilirubinemia, hemolysis, hypertriglyceridemia, antibodies, especially for immunoassays, and some degradation products, metabolic molecules, exogenous substances, and sometimes anticoagulants. So there are list of substances which can cause interference, but here I have listed only common substances which can cause the interference to our analytes or the technique. So I think we had a good lecture with immunos interference. So there are a list of causes for immunos interference such as heterophile antibodies, nowadays biotin interference, so cross-reactivity of steroid hormones, and for the cortisol assays, the cytochromes, analog methods, and there are substances which we don't know. So there are a lot of substances which cause interference to our studies, our techniques, our methods, but we couldn't identify those things. And potential interference factors may be checked by analyzing samples to which solution containing suspected interference substance. We can add this. And especially this hyperlipidemia, hemolysis, and bilirubin, generally it is concentration dependent. So if the interference is more, when it is concentration is more, these substances, it is most of the time it is concentration dependent. So what we can do is, when we are doing this interference studies, we can have several concentrations and then we can conduct the interference studies. So the important thing to avoid to the matrix undisturbed. So the amount of solution added has to be less than 1/10 of the sample volume. And when you are selecting the concentration of interference substances, better to select for the highest possible concentration compatible with life, right? So that when you are selecting it, it is important. We have to select the highest compatible concentration for that analyte, right? And so nowadays, most of the techniques, nowadays it is, I think, very few interferences. And you all know, especially for biochemical newer techniques, newer analyzers, they have hemolysis index, lipemia, and icteric index. So if you function it, so you can see if your sample is hemolyzed, so they will report it as the index. So it is important to find out this abnormality present in the testing. It could be due to hemolysis. So that is important. If it is available in your analysis, please function that, and it will be really easy rather than looking each and every sample very subjective, and it will be changing. So that is now available. So we can prevent, and we can ask for a fresh sample, or we can send the report with the comment. Few things about the limit of blank. So what do you mean by limit of blank is the lowest concentration of analyte that can be differentiated from 0. So that is LOB taken from mean blank plus 1.645 SD blank. So that is how we detect the LOB. And how we take the blank sample. So this blank sample has to be similar to natural patient sample. And we can measurement, we can take number of blank samples. So how we take the blank sample, so we can use precipitation techniques by antibodies or by enzyme degradations or adsorption to charcoal, or some of the hormones if the patient is diseased, or suppressed, we can use that sample. And when the patient is having no tumor, if you are using for a tumor marker, we can use that sample. So depending on the analyte, the different types of analytes, you can take a blank sample. And limit of detection. So what is limit of detection? Is the minimum concentration of the analyte whose the presence can be quantified by under defined conditions. LOD is equal to LOB plus 1.645, which is the SD of the low concentration sample. So LOB, and this is LOD. And there's another term known as limit of quantification. So that is also the lowest concentration the analyte can be not only by reliably detected, but there are some predefined goals. For example, you can have a concentration at which we can use a CV. So at a CV of 20%, what is the lowest concentration we can detect it on that analyzer, right? On that method. So that is the limit of quantification, or sometimes known as the functional sensitivity. So clearly you can see this one, limit of LOB, limit of detection, and the functional sensitivity. So that is how this will come. So first, limit of Planck or limit of absence, and the limit of detection, the next step, and then the functional sensitivity with the CV. And is it important? Yes. So limit of detection, limit of quantification are medically important in certain analytes, especially for hormones, right? So, so that is reliability distinguished from 0 is the LOD, but not necessarily for all the analytes that is required, right? So there are some great importance in the trace and ultratrace methods when the concentration, the lower concentration or LOD is important. For an example, TSH, tumor markers, and PCR. So if you use this, the analyte concentration much higher than the LOQ, there is no point finding out the LOD and LOQ. So there, it is not necessary for all the analytes. So it is required especially for some of the analytes only. Yes, that's all. I'm happy if you have any questions.
Thank you very much, Dilika, for that nice presentation. And if you have any queries or doubts, Dr. Dilika will answer now.
Hello.
Yeah.
Majita here, Dilinika.
Yeah.
Can you go to that your slide of measurement of uncertainty and the bias? There was
Okay. Yeah, here.
so the accuracy in the closeness of agreement between the results of measurement and true concentration. So it's influenced by the bias and imprecision.
Yeah.
I am not sure. Can you little bit elaborate on this? The accuracy quality term inversely related to the uncertainty of measurements.
Yeah. So if the accuracy is like, if it is accuracy is low, it is inverse related to the uncertainty. So when the accuracy goes down, it is uncertainty is up.
No, no. What about this then? There's a previous one before this.
Which one? This one.
Yeah, this a difference with average value to express numeric inversely to the
So
trueness.
that,
Yes.
yeah, that is the trueness. The trueness is we are taking from the agreement between the large number of measurements and the true value. So that is the trueness.
Yeah, that is a mean of the our readings.
Yes, so that is the we take we take the large series of results compared to the accuracy. We take only one result to the target value and our result.
Oh, the next one
Is the accuracy.
Yeah, this one accuracy. So this is the whatever the difference coming is going under the term of uncertainty of measurement.
Yes, that's right. Yes, yeah.
Okay. Thank you very much.
Okay, sure.
Any more questions? Okay, there are no more questions it seems. Thank you very much, Dilnika.
Thank you, Dr. Tushara. Yeah.
Now I invite Dr. Dilanti Varavita to deliver the vote of thanks.
Thank you, Dr. Tushara. So we have reached the end of the Trainee Day Workshop series organized by the College of Chemical Pathologists. Before winding up the session, let me thank all the speakers who delivered very informative and interesting lectures amidst their busy schedules. Thank you all, and we expect your support in future events also. Further, I would like to thank Dr. Tushara Devagigana for organizing and moderating the workshops, Dr. Isali Hekmutapadu for the guidance given, and Dr. Daya Patulanda for suggesting very interesting lecture topics. Next, our sincere thanks go to all the participants who joined and encouraged us today. Finally, let me thank Ms. Madhusha Utkala, the coordinator of College of Chemical Pathologists, for the support given in conducting this session. And a small note is the links for the feedback forms will be sent you via email. Please be kind enough to respond by filling these forms when we send it to you. And so I would like to thank all the participants and all the lecturers and all who supported this lecture series, and hope to see you in another event like